Okay, so what were we doing? Okay, let's start. So in the last class, we introduced Hilbert spaces. Can you hear me properly?
Yes, sir.
Yes, sir.
Yes,
Yes,
sir.
sir.
So
Yes.
I'm switching on my fan. After that, also you tell me whether you can hear me. Okay, it's fine. Anyway, I'll bring my laptop.
Yes, sir.
Okay.
It's
Yeah, yeah.
fine now.
Okay, it's fine. Okay, so last class we were discussing Hilbert spaces. Okay, so we introduced Hilbert spaces and then we introduced orthogonality and we proved the following. If we have a subspace M contained in H, a closed subspace, okay, it's coming there. Yes, very good. It's coming there. So if you have a closed subspace contained in that, okay, then H equals M direction in whatever the sense. Okay, in the sense that M and M per orthogonal in the Hilbert space direction, and every element in H can be written as something in M, some plus something in M per, so that they are orthogonal also. Uniquely, they can be written like that. Further, we proved that for the closed subspace, M equals M double per, okay, which is equal to M per, okay, by definition. This is definition. So after that, I said something, but I was unnecessarily confused. So let me just do that. So if S is a subset of H, then S double perp, S double perp, is a perp of. I mean, the perp you can define for any subset. It need not be a subspace. You can define for any subset. Then this is equal to span of S. You take span of S, and then they take the closure in the inner product in the norm. And this is just clear because if you take S perp, which is also same as span of S perp, span of S closure perp, okay, you call it M. You call this as M. Then you know that M double perp equal to, I mean, sorry, this I want to call it M. I want to call this as M. M equal to span of S closure. Okay. Then we know that M double perp equal to M for closed subspace. Okay. So this implies span closure of S equal to M. Okay. That's all. I mean, M double perp is S double perp. Sorry. So the smallest closed subspace containing any set is just the double perp part. I mean, I'm just using the fact that in this, I'm just using the fact that if you take any S, then the S perp is also same as span of S closure that perp. That's because if something is orthogonal, say this we can prove. I mean, if you take any S, take any S contained in H, then this is what I have used. S perp equal to span closure of S. Okay, this is clear because S is contained in S is contained in span of course span of S closure. Okay, this implies span of S closure per contains S per. Okay, because if something is orthogonal to a bigger set, then it is orthogonal to a smaller set. Okay, so sorry, it's the other way. I wanted to write the other way. Okay, if something is orthogonal to a bigger set, then it is orthogonal to a smaller set. So something is contained here, then it is contained here. Something is orthogonal to this bigger set, then it's certainly orthogonal to a smaller set. Okay, so this perp is contained in this perp. So that is clear. On the other hand, if some x is orthogonal to S for all S in S, then x is orthogonal to all y for all y in S. I mean, it's just clear span closure of S. So this implies the other inequality. This implies span S closure contains S. Okay. So this is what I used there. Okay. Anyway, it's trivial. I just wanted to give any proof. That's all. Okay. So this is about orthogonality. Then we want to define what is called an orthonormal basis. So before defining orthonormal basis, I want to say what is an orthonormal set. So some EI, where I is indexed by some set I, okay, contained in H, is said to be orthonormal if the inner product between EI and EJ equal to delta IJ, okay, for all IJ, sorry, IJ. Okay, so if I is equal to J, then it's norm. I mean, then EA inner product J is the norm square, which is 1. And when I not equal to J, it is 0. Okay, inner product EIJ equals 0 if I not equal to J. That's what it says. Equal to 1 if I equal to, of course, if otherwise I equal to I equal to J. Okay. So this is what is called an orthonormal set. Okay, an orthonormal set EI, INI is said to be an orthonormal basis. Is an orthonormal basis if it is a basis, of course, orthonormal basis, but it's not usual vector space basis. This is the shorter basis. If span closure of EI, INI equal to H. You take the span of all elements. By span, I always mean finite linear combination. You take finite linear combination. So it's a vector space span. And then you take the closure has to be H. So this is what is called an orthonormal basis. Okay. So the definition of orthonormal basis is clear. Okay. So I want to give an assignment. This is in Banach space, this assignment. The assignment is the following. So if you have a family of Banach spaces, let Xi, INI, this can be uncountable. I mean, this here also the indexing set can be uncountable. There is no assumption about I. I can be countable, uncountable, finite, or anything. Okay. Okay. So let Xi, IN be a family of Banach spaces. Then there are several ways of making a Banach space out of this collection. Okay. So let P be less than or equal to infinity, greater than or equal to 1. Then you define, so let, so I want to call something summation Xi is just notation. Okay. Summation Xi is just a notation, is equal to all those just finite linear combination I want to say, but there is no, they are all not contained in something. So I want to say that you just take this, I mean, Xi1 to Xin, okay, Xik is contained in Xik. You take this finite, I mean, it's a direct product, but you take only finite tuple. Okay, you allow only finite tuple. So this is that. This is the summation Xi. This is just a notation. Okay, definition by definition. You define summation Xi to be, you take finite tuple, finite collection. But then this I is varied over all those I. Okay. So you take Xi1 up to Xik or something, where Xi1 up to Xin maybe. Okay. With Xik is contained in Xik. Xik contained in capital Xik for K between 1 to N. Okay. So this is clear. This is just summation Xi. This is just a vector space.
Sir, is N fixed or is N also variable?
Say it again.
Is N in this definition a fixed natural number or is it a
no, N is not fixed. You take any N, any number of N.
Oh, okay.
It is just finite. That's what I want to say.
So like the tuple can be of any number of elements.
Tuple can be any billion time. I mean any large. Okay, it doesn't matter. It's just finite. You take finite collection, finite tuple. Okay, all possible finite tuple you take using this
Okay.
with the xik is an xik. Okay, that's all. You take all possible finite tuple, then define norm of any xi 1 up to xi n. Okay. P, I used P or K, P equal to summation. This norm is defined xi k norm over P whole power 1 by P. Okay. Then, I mean, it's clear. You can prove, we have already seen, you don't need to prove. Then norm P is a norm. Of course, this summation xi is a vector space, of course, is a norm on summation xi. Okay. Then we define, so define direct sum to make, I mean, there is a P involved, so I keep this P here. Maybe I shouldn't keep the P up. Okay. P of I in I of all this xi equal to summation A xi to take the completion. Okay. Completion with respect to that norm. You know completion, all of you know the completion with respect to metric spaces. Okay. It's just a metric space completion. Completion with, you have a norm that gives a metric space. There is just a metric space completion with respect to that norm. Okay. So what is that? We have just defined something. We haven't proved anything. Okay. Now the proof is, what we have to prove is the following. Now also you define, so this is one way of doing. Okay, prove that this direct sum P I in I. So till now there is nothing to prove. I have just defined something. Okay, I in I xi. This space is isomorphic. Isomorphic mean isometrically isomorphic. There is a bijection which preserves the norm also. Okay? Isometrically isomorphic to this, all those x tilde in, this is the direct product. Okay, I in I xi. This is the direct product. You can take the direct product of any connection, whether it is uncountable or something. Okay, such that summation this x tilde is a, so x tilde has an I, so xi. So I mean, you have to define it for infinity also. Infinity, you take the L infinity norm, okay, the supremum. So I will say that for P equal to infinity. Let me write it and then tell you. So here it will be again the supremum for infinity. So I is fine. Okay. Okay. This is a vector space. I take all x tilde where x tilde equal to this tuple xi. Okay. So this is very easy. Actually, through it's, I have written it through it looks long, but it's very easy. I mean, you can directly verify. There is really nothing in this. I'm just saying, you take a collection of Banach spaces. If you wish, you can take it to be countable. I don't mind. Okay. Then it's a family of Banach spaces. Then you define summation xi as taking finite tuples from this xi. Okay. Then you define a norm on this finite tuple on that vector space, the pth norm. Then you take the completion. You call that as the direct sum of xi. I'm saying that is precisely equal to, you know what the map is. Okay, in the direct product, you take finite tuple, map it to the finite tuple here. This direct product has finite tuple also. No, to make sense of finite tuple, you need to fix other things. You can take 0 everywhere else. Okay, in the tuple, you take 0 everywhere else. Only in the finite place, if you have xi1 up to xik, map it in the direct product with 0 everywhere else, and then take xi1 up to xik in the finite, in the finitely many places where it is there. Okay, so that is a map, of course. Then you have to say that the norms are mapped precisely. And here it is precisely that here I'm taking this is the direct product. The direct product is the infinite tuple. Okay, In that infinite tuple, all those tuples such that when you sum it, it has to be finite. So in particular, this sum, whatever this tuple, infinite tuple, this cannot be uncountable. You have to have only countable tuple. In particular, if you notice, because that sum is finite, in particular, I mean, any x tilde is here, then if x tilde is here, then xi equal to 0 except apart from maybe apart. Countably many. Okay. So it cannot be non-zero for uncountably many I. Then the sum will not make sense. Sum will be infinite. Okay. So this is the assignment. The assignment is clear. Okay.
Yes.
Okay. So that's the assignment. It's not difficult. It is just to convince.
Sir,
Yeah.
how are you defining the vector space structure on the summation xi?
Summation xi. That is just you add over R. Okay, you have to have you sum over the corresponding xi. I mean, if you take xi1 up to xik, you have somewhere else. Then you concatenate it. Then I mean, it's clear how to do it. I mean, you can sum it in this direct product if you want. I mean, you can have then it's.
Sorry, sir, your voice is breaking, I think.
My voice is breaking. No, one second. Let me look at my. Sometimes it gets connected to some mobile. No, it's in the right internet connection. Is this okay now?
Yeah, now it's better. Yeah.
Okay, yeah.
Sorry, I couldn't hear. Can you kindly repeat?
Yeah. So how will you sum? That is the question. So if you take any tuple, if you take another tuple, you concatenate both the tuple. I mean, you take a bigger tuple, okay, wherever there is an intersection, you just sum between them. Otherwise, you just take it. It's just clear. No? You take xi1 ixin and yj1 to yjm. Okay.
Sir.
This plus things, you have to write it as wherever there is an intersection, you just submit. Otherwise, you just keep it as a tuple. But then there will be a. So what I would suggest is you consider this as the subspace of that finite tuple. I mean, okay. Consider this as then the sum is clear. No? All you have to prove is it is just precisely these things. I mean, it will be all the elements. The completion is nothing but precisely those things which are summable. That's what I want to do. Okay. Consider summation xi containing in this. Then it is summable. Okay. Then you can make sense of the sum. And that is what I want to do. Okay. As a subspace of this. That means
So like in the definition of summation xi, can't we say that those are precisely those tuples which have finitely many non-zero terms?
What is that definition of? Say it again. What did you say?
Yeah, I was saying that in the definition of summation xi, I mean that thing can't we define as the subspace like tuples which have only finitely many non-zero terms.
Exactly, that's all. You take summation of xi as some come with the. I mean, if all those vectors x tilde, this is equal to all those x tilde, such that x tilde is non-zero only for finitely. Only in finitely many places. Finitely many. Okay.
Yeah.
So there you define the norm and then do that. I mean, it's all clear. You just have to write it precisely. Okay, that is the assignment. Okay, there is really nothing to prove, but it's just to convince yourself. I mean, it is in fact, I want you to ask those questions and write it clearly. That's all. Okay. Okay. So now if we have an orthonormal basis, now let EI orthonormal basis, which I write it as Y and B for a Hilbert space H. Okay. Whenever I say orthogonal this, it has to be Hilbert space. Then, okay, I want to define internal direct sum also. You can define internal direct sum. Similarly, so this is definition. Okay. You can define it for a Banach space in the same way. Let me define it for Hilbert space. Okay. Let Hi a family, Hi, I in I, a family of closed subspaces of our Hilbert space of closed subspaces Hi containing H of H. Okay. Then direct sum I in I, Hi is equal to H, okay, as a Hilbert space. So that says that, I mean, as a Hilbert space means you take summation Xi with Xi in Hi, its closure equal to H. That's what it means. Okay, that's what it means that it is a direct sum. Direct sum means you take summation Xi, then you take the closure with respect to LP that is equal to H. But then this is precisely all those Xi. This is precisely all those summation Xi. This is equal to this. I mean, without the closure, I'm just saying this is equal to all those summation Xi. I equal to I in I. I mean, here it's finite sum. I'm sorry. Let me write it again. I'm defining the direct product. I mean, I'm defining the direct sum as you take finite sum. Okay, summation Xi, maybe Xi k equal to 1 to n. Okay, Xi k is in Hik with k less than or equal to 1 less than or equal to 1. You take finite sum like this from Xik in this and take the closure. And by the assignment, this is precisely equal to summation Xi I in I with summation norm Xi square, the Hilbert space norm. Okay, this is the Hilbert space norm, and that's why I put a 2. Maybe I have to move it. It's fine. Okay. We do the assignment, then it is clear that this is same as this. Well, there is some work you have to do in the assignment, but I mean, show that it's isometric, then this is same as this. This is clear?
Sir, P is 1 right here. So why are we taking the norm squared?
No. There also P, I mean, P is not 1, P is 2 for Hilbert space. Hilbert space P. Hilbert space, the direct sum norm, you use 2, not 1. If you use 1, that is the L1 norm.
Okay.
Right? Okay. Hilbert space is always square. Okay?
Yes, sir.
Yeah.
Okay.
So then what I want to say is the following. If EI
Summation of this norm square, this you are defining only when countably many things are non-zero?
No, uncountably it cannot be non-zero, no? I mean, it cannot be infinity, smaller than infinity, no? By this, I mean, see, how will you define for uncountable? See, I see you have to make sense of uncountable. How will you make sense of uncountably many of them? I'm not going through those details. If you want to define for uncountable thing, you have to take a finite net. I mean, you have to define a net. You know net? Have you studied net? You have to take.
Yeah.
So you have to take nets. So I don't want to go through those details. So that's why I'm saying if you want really, you can work with uncountable. Okay. But if you want to do it, really do it for uncountable, then you have to define through nets. That's what you have to do. You have to take something like this. You have to take this to be all finite subsets. Okay. F contained in I finite. You take all these things. Okay. Then you define So if you want to talk about summation fi, then you want to define SF to be summation I in F xi. Okay, you want to define some SF like this. So this is a net SF. This is a directed set. I don't want to do this thing, so that's why I didn't do directed set. Unless really it's needed, I don't want to do. This is a directed set. Okay, now this SF with F in this net. This is a net. So we say that summation xi, or even for infinite thing, converges if SF converges as a net. This net converges. Okay. Okay, that's what it means. If that net converges, then xi has to be, and if that net, this absolute sum converges, then that has to be only for countably many of them, they will be non-zero. One can prove that. Okay. So I don't want to go through all those nets and all those things. So that's why I'm saying, if you really want, you can consider nets and get convinced these things. Otherwise, do just assume that it's just countable. Because we will not be dealing with non-separable Hilbert spaces. We will be dealing with separable Hilbert spaces. So this is fine. Okay. All our later theorem, everything will be for separable Hilbert spaces. Okay.
So like we can take I to be countable in the assignment?
In the assignment, you can take I to be countable if you want. If you want really to do something complicated, don't. It's not strictly necessary in the assignment to take that. You can use this statement. If that's finite sum is infinite, then if it is finite, then it's non-zero only for countably many I. You don't have.
So we can assume this result.
You can assume that, yes, which can be easily.
Okay.
Okay. If there is a complication of net or something, then you can just assume it's fine. Okay. I don't think there is any such complication.
Okay.
Okay. So I am just saying that if you have a HI is a Hilbert space, then I have defined internal direction. Internal direction is you take formal sums like that, and then you take formal sum like that. Then you here also when I said Banach space summation xi, you can just take formal sum, and then you can sum it. You can write it to summation whenever there is a possibility of summing. You can sum anyway. That's all. So you can just do that also. You can write formal sum. But here also you take formal sum like that. You can take some sum like this, summation xi. Then you just take the complete closure of that with xi in that, and you take the closure. That is the internal direction of Hilbert spaces. That is precisely equal to all those summation xi. By the assignment, it's clear that that is all those things summation xi with summation norm xi square smaller than. Okay. So from these things, it follows that if all these things imply the following: if ei I in I is an orthonormal basis for H, then H is equal to direction CEI. CEI is just a one-dimensional subspace. EI equal to lambda EI, lambda EC. It's just a one-dimensional subspace. Okay. This is clear. That is, H is equal to all those summation lambda I EI with summation mod lambda I square equal to this finite. This is because, that's clear. The norm of lambda I square is this. It's fine. Maybe I will prove something more about all these things. Well, so we have already, I think we have already noticed. So let me make some properties of orthonormal. So whatever I have said, is that clear? Any Hilbert space is just an orthonormal. It's a direct sum of CEI. That is because each CEI is orthogonal. CEI is orthogonal. That's because CEI, this vector space is orthogonal to CEJ if I not equal to J. Okay. And I'm just saying that summation lambda I EI. When we say something is an orthonormal basis, EI is orthonormal basis. implies that summation lambda ei, finite sum, finite sum. The closure equal to h. That is the definition of orthonormal basis, right? So it's precisely that. That's what I have said here. If you have internal direct sums, I mean, this is true for not for one dimension, it's for general subspaces. Direct sum I, direct sum hi, internal direct sum, you can define it like this, which is precisely equal to summation of xi with summation of norm xi square is smaller than 50. So that's why I'm saying if you take an orthonormal basis, by definition, an orthonormal basis is an orthonormal set. Their EI is orthogonal to EJ. So CEI will be orthogonal to CEJ for when I not equal to J. And if you take finite sum like this, then the closure is H. Okay, so that is equivalent to saying H is all those things, summation lambda EI with summation lambda I square is finite equal to H. Is this okay? I don't see anyone here. It's fine.
Yes, yes.
Okay.
Yeah. So we are assuming only countably many non-zero to make sense of this sum, right? To make sense
No,
of
you
this.
don't need. That's what I was saying. No, you can make this sum even if it is uncountable using these nets. Where was it? I said no. You can you use this net. That summation xi converges if this is net sf if this converges. That's it.
Okay, so but then like how does that imply that only countably many things are non-zero?
You work it out. If it is positive and other thing, it's clear that because it's equivalent to saying that you have an increasing net. Okay, increasing subnet or something, which will be that you have to work it out. Okay, I mean I don't want to go through all those details. That's why I haven't defined all this net. I defined this direct sum and directly do it. Okay, if you work it out, you will get it. It's not difficult. I think in Sundar's book itself, in the exercises, it's given something. From that, you follow. You do those exercises, it's in the exercise. If you do those exercises, it will follow. If you can't get it, we will do it. Okay. Now let us proceed. For countable, if it is clear, let us proceed. Okay.
Sir, I had a question regarding the direct product. So, I mean, is there some inner product you are defining on a direct product?
Yeah. I mean, yeah. Well, I define norm. I'm not defining inner product. You take the usual inner product, just the sum of the inner product. That's all.
No, but like in the direct product, I think you can have. I mean, at least in the vector space situation, called by direct product, we mean arbitrarily many terms can be non-zero.
Arbitrarily many
terms can be non-zero, right? In direct product.
No. Direct product is arbitrary sum, but when you define the inner product, it will be only. I mean, you will take finite sum, define the inner product, take the completion. That is the Hilbert space direct product. You have Hilbert space. Okay, you have Hilbert space. Okay, you want to do this. It's the same thing. Hi. I and I. You have Hilbert spaces like this. Okay, then you can define the direct. You can define x1 up to xi1 up to xik, y something. I mean, you can take finitely many of them. I mean, you can take all those things which I mean, you take x. I mean, you can define the direct product like this. If you take a tuple like this, I and I. Something has happened. I and I. And you take yi, yj, yi, I and I. You take the inner product, just this summation xi, yi. But this is only finitely many. I mean, finitely many non-zero. Both this xi and yi, many non-zero entries.
But in the, I mean, in the definition of direct product, shouldn't arbitrarily many things be non-zero?
Wait.
Okay.
You take the finitely many thing, you just define it like this. Then you take the completion. You take finitely many tuple with only finitely many entries. Then you define the inner product as summation like this. Okay. Then you take the completion. That completion is precisely all those things. By Cauchy-Schwarz inequality, the inner product will be well defined. Summation mod xi, norm xi, yi. If you take countably many also, that is less than or equal to summation norm xi, norm yi. That is less than or equal to summation norm xi square whole power half, summation norm yi square whole power half. So this is final. If xi satisfies this condition, yi satisfies this condition, then this inner product exists. Okay?
Okay, sir.
Yeah. Because of that, the inner product exists. Or you can directly define like this. Yeah. You can just directly define this sum, and that exists because summation xi square is finite, summation yi square is finite, summation norm xi square is finite, summation norm yi square is finite. Because of that, it will follow. Okay? Now it's clear?
Yeah.
Yeah, now it's clear. So the inner product exists on that. Okay. So in that sense, I'm saying that this H is direct sum of summation EI. That means it is just all those summation lambda EI with summation lambda I square is more than. Okay. Now let us just do some. Now let us just write some properties of inner product and other things. So the first thing is, so let me say that EI is an orthonormal basis. What is this? I want to prove some Bessel inequality or something. Okay. So the first property, 1, if you have some x in H such that x equal to, can you see it here? I am not able to see it here.
Are you writing something now?
One second. What happened is, when I was talking, I sprayed on this, so it's not writing there. It's not erasing also. Okay. Okay. Let x in H be such that x equal to summation lambda I EA. Suddenly not writing there. I don't know why. I mean, for some kind of summation. Then it's clear that x ei, the inner product, equal to that lambda I. That is just clear, right? You take the inner product with the other ej, the inner product is 0, so it will just look like that. So this is clear. Okay. The second property, because we may be using this again and again, x. So if x looks like that for any, so this is second property has nothing to do with the first property. I mean, the whatever x looks like that, I'm not saying like that. Xb, if x looks like summation lambda ei, then x inner product ei is that lambda ei. That is clear, right? Okay. The second thing is, if x is in H, okay, then any H, any x may not look like that in the previous observation. Then summation x ei, you take the inner product with ei, okay, and ei, here, then x minus this is orthogonal to ei. Okay, this is this need not be an orthonormal basis; it's just an orthonormal set. I don't know what happened to my pen. second. Now I think it writes well. Okay. Yeah. So, okay, this is clear because if you take X inner product with EI, I mean, if you call this as Y, okay, I want to say that this is orthogonal to EI. If you take Y inner product with EI, okay, that is equal to XEI minus, if you take the inner product with that other, I mean, except I, everything else will be annihilated when you take the inner product. It will be 0. The inner product is 0. So XEI. That is equal to 0. Okay. This is clear. It's fine. It's fine, I believe.
Yes, yes, yes.
Yeah.
Then there is something called, this is called Bessel's inequality. Just the name, it's simple thing. Okay. Which says the following: summation mod XEI for all X in H, summation mod XI EI square I in I. For any orthonormal set, this is true. Is less than or equal to norm X square. This is just because you take Y equal to X minus summation I in I XEI. Okay. Then we have by 2, Y is orthogonal to EI for all I. Okay. So Y is orthogonal to, in particular, Y is orthogonal to, implies Y is orthogonal to summation XEI EI, right? But then summation XEI EI plus Y equal to X. Okay, that's how Y is defined. X equal to that. That's from here. Okay. But then these two are orthogonal elements. You know, orthogonal. I mean, this is clear. If X equal to, I think I have already said it. X equal to Y plus Z, where Y is orthogonal to Z, then norm X square equal to norm Y square plus norm Z square.
The Pythagoras theorem, we proved it last class.
Yeah, we have, yeah, Pythagoras identity or something. Maybe not theorem. Okay, identity or something, which follows from, if you put the inner product structure, then the Pythagorean theorem follows automatically. Okay, so that follows. So because of this, from here we get that summation norm xi x summation mod x ei square, which is the norm of this, plus norm y square equal to norm x square. So in particular, summation, this implies summation mod x ei square. This is smaller than or equal to square. This is true for any orthonormal set. Okay. Okay. So that we have done.
Sir, when you were defining this y as x minus the summation inner product xci times ci, so like, don't you need to check that the sum is well defined, or like is unconditional summation?
But when it is less than that, it's clear, no? You are proving that it
I
is
mean,
less than something.
so you are essentially subtracting
No, when
some...
the first one, the first one. First one is well defined. Suppose if it looks like that, that means it's well defined. It converges also, you are assuming. Whenever you write something, the first one, whenever you write something, it's well defined. That's what we are assuming. Suppose if it is well defined summation.
sorry, what do you mean by first one? I didn't get it.
The first one. No, in the observation 1, you are asking. Here.
No, observation 3, like where you are taking the no, not there. That is fine. I was talking about this third observation.
This is less than or equal to this. Okay.
No, where you are taking this, where you are considering
here
this.
I'm taking the summation. That's right. So here I'm taking the summation like this. Yeah, formally I'm taking it like that. So
Yeah, that should be, I think one should say that it is unconditionally and convergent and stuff like that.
Correct. Yeah, so I have to prove that. But that is just clear, no? That is clear because you have an orthonormal set. Okay. So maybe we will prove that. See, we know that for any orthonormal basis, it converges. See, any orthonormal set can be extended to an orthonormal basis. So your question is right, valid question. So let me prove this. The following. Then it will all be clear. If EI, so this is just a lemma or something. Maybe this is a proposition. Let me use proposition. This is John's lemma. So if EI, I contained in I, is an orthonormal set. Set in H. Okay. Then there exists an orthonormal basis E, maybe call it J, orthonormal basis. I call it EJ, J, with J contained in I. Okay. I mean, that means it contains EI. Okay. So proof, this is just John's lemma. I mean, you take all orthonormal set, take all E contains this EI, is orthonormal. Then you define E is less than or equal to F if E is contained in F. Okay. Then it's clear, it's every totally ordered set, you can take the union and every totally ordered set. Clearly, every totally ordered set, there's a, yeah. Then it's clear that every totally ordered set has a upper bound. You just take the union. Okay, I don't want to write. Okay. Then by Zohn's lemma, there exists maximal element E naught or something. So if E naught is not an orthonormal basis, that is span closure of E naught is contained but not equal to H, then choose. I mean, then it's clear that the orthogonal complement is non-empty. If the orthogonal complement is 0, then the double orthogonal complement will be equal to that. So because of that, it's I mean then the then the span E naught per is not equal to this. It's bigger than that. Okay. So choose X naught orthogonal to that. Okay. In X by X naught. Add with that singleton this. Is an orthogonal. Is orthogonal, which is a contradiction. Okay. So it contradicts maximality. What I'm saying, yeah. Suppose if this is not true, this is orthonormal, contradicts maximality. E naught. Okay, so E naught is orthonormal. It's fine.
Yeah, this is fine, but like, how does this
So the
show
same
that sum is unconditional?
that every orthonormal basis, everything can be extended to an orthonormal basis. Okay. Now, so this is okay. Now, if X is in H, okay, if you have any orthonormal set, EI, I in I is orthonormal. Normal. Then there exists EJ, where J is in some J containing this EI, orthonormal basis. Then for every, then for all, we have noticed, we have said that we have noticed, or we have proved it. Once you prove the assignment, notice that H is equal to CEI direction. J in J. Okay. So this implies XEI. H looks like this. X in H implies X equal to summation lambda I EI for some lambda I. Okay. Then by whatever we have noticed in 1, then this lambda I equal to XEI. Okay. In particular, X equal to summation XEI EI. This implies summation mod XEI. So this makes sense for anything. This for alpha. So this makes sense. This makes sense for an orthonormal basis. Okay. So every element, this makes sense.
No, but like, how does this like exclude the possibility that if you like permute this collection, then you won't be getting some different X? This is a like arbitrary summation, right? And
No.
I think that needs to be checked. Like if you permute it in any way, you will get back the same X, and then it is
No. This is absolutely convergent. This is absolutely convergent. Okay.
No, its square is convergent, right? It is not. The mod of that thing is not convergent. The mod square is convergent.
Yeah, but that will imply that also. Summation. What do I mean by, maybe it's contained in the assignment. Let me see. What do I mean by summation? It looks like X equal to summation XEI EI. That's what I have defined it like that. I am see, even for XP, that's what I'm saying. That's the part of the assignment. It is all those things, sum like that, such that the summation is, then you can define the summation. Now, what is the problem? You want to say that X minus this converts to 0. X minus summation XEI.
No, what I am trying to say is, so suppose in the case of real numbers.
No. This you want to say, no. For any finite thing, you want to say that this net goes to 0. That's what you want to prove.
Yeah. I think that thing should suffice for this.
By this we mean that this net converges. Okay. Forget about uncountability and all. Even if it is uncountable, we just need, by this we mean X equal to summation, whatever, summation, maybe I will digress here. X equal to summation Xi, I in I. Means you form finite net like this, Xf, F in some finite thing. This converges to X. Okay? Where F is, this is all finite subset of this. F contained in I. Finite. F finite. Okay? This net converges to this.
No, like, so actually my question was, so actually my question was based on this thing. So suppose like if you consider real numbers only, then you have this series like 1 minus half plus 1 plus minus 1 4.
Forget about real.
This thing.
I'm just saying that if summation mod xi square, whatever, this is finite, then this net converges. Okay, this should be an exercise, or I should write it. Then this net converges to this summation.
Yeah, okay, yeah. Yeah. Then this should
be clear to you. Now it's not clear to you.
Yeah.
What? Yeah. It's clear to you.
Like when,
I'm
like
just
initially when I had
when this
learned this thing, like
when this condition satisfied, then the except converges. That's what I want to say. That is, you take I mean, this net will converge. That's what it means. You take summation. I'm just saying you take summation ei. In this case, summation xei ei. Okay. This means take finite net that will converge to that. Is that clear?
no, yeah, I mean, when I had first read this thing, I mean, there was a result that only finitely many of these inner products will be, only countably many of these inner products will be non-zero. And then this sum was
That
just
is
a
certainly
countable
true.
sum, and
That is
things
certainly
were easier. I mean, that was a separate.
correct. Well,
Yeah.
these things are very clearly done, and I thought I will avoid that net and other things, which is done in Sundar's book. Maybe I should ask someone to present, or it's all very simple things. There, the unconditional summability and this conditional summability, these things are compared very neatly, and but you have to go through nets. Then I wanted to avoid nets, but I have maybe if you use countable things, then you don't really need it. I'm just saying that if this is true, then this converges. All you have to make sense is x minus this summation. If you take any finitely many of this, some infinite sum of this x ei, this norm will converge to 0. That's what you have to do. Okay, maybe 1 second. Let me just look somewhere. I have the book somewhere here. I thought I will avoid this and do something. Yeah. Is there anything I have missed here? Okay, so next presentation, this is just very easy. Just present proposition, then it will all be clear. I have already given enough. I mean, I have almost done. If you prove that assignment, it's all clear. Presentation is this proposition 2.35.5 in Sundar's book. This is not the measure theory book. This is functional analysis. I think the title is functional analysis. Spectral theory. Okay. Just prove this proposition. Whatever is needed for the proposition, you will need some other things there. Just make use of that and then prove this. Okay. This is the presentation. Someone should present this one. Then it will all be clear. Okay, now itself it's clear except whatever I have said here. One has to prove this. But this proof is contained in there. Okay. So someone should prove this. So it's good you ask this question. So this is done. Okay, so I don't want to spend time on this, but if you, so in that, I have changed the thing. I have to find it. Anyway, let me not look at it. So from that, it will be clear that if you have any element x in H, then x equal to summation x ei. You can write it like this, and with summation norm or mod. This is just mod. Mod x ei. smaller than 50. Okay. If you have 2x and x and y in H, okay, then inner product xy equal to summation x di and diy. Okay. I mean, this is just sum of complex numbers. So these things will follow. Yeah. Okay. So, I mean, we don't have much time. So these things will follow from that. Okay. So someone should present this so that we will go through it systematically. Okay. So this is about orthogonality. Then I want to do something else. No, there is something more. I have to prove this following proposition. So following two statements are equivalent. H is separable. Separable if and only if there exists a countable orthonormal basis. So we have already said that if you have an orthonormal basis, you can extend to an orthonormal basis. Okay, and there are, I mean, if you have an orthonormal set, then you can extend to an orthonormal basis. So we always have some orthonormal, non-empty orthonormal set. You just take one element, just divide it by its norm, then you have one orthonormal set. Okay, so there always exists an orthonormal basis for a Hilbert space H. Okay. So we don't need to talk about existence. We have to only prove that orthonormal basis is countable. Okay. So first statement: if H is separable, okay, let Xn n in M is dense in H. Okay. Then I want to find then I want to prove and suppose. I mean, the existence of orthonormal basis is clear, I believe. Is that clear to everyone? I have already proved here this answer. If you have an orthonormal basis, okay, then there exists, if you have an orthonormal set, then there exists an orthonormal basis which extends that set. Okay. In particular, maybe I will write it here. There exists OMB for any Hilbert space. Okay. You take just one element and divide it by its norm, you get an orthonormal set that can be extended to orthonormal basis. It's fine. It's okay, no?
Yes.
Okay. So
Yes, sir.
okay, if H is separable, then I take a dense set. Okay, then I have an orthonormal basis also. Suppose EI, I and I is orthonormal basis for H. Basis for H. I want to say that this EI is countable. Okay. Now consider the distance between EI and EJ. So for I not equal to J. This is square. This is equal to EI square equal to norm EI square plus, this is 1 plus 1 minus 2 times real part of EI EJ, which is 0, of course, so which is just 2. Okay? This implies EI minus EJ equal to root 2. Okay? They have a fixed distance between them. Okay? Now find Xi in the ball around EI divided by 2. Okay, 1 by root 2 divided by 2. So you are finding, I mean, then the xi's are distinct. It's clear. Then I going to xi is 1. Okay. If xi equal to xj, then xi will be in ei. It cannot be in some other ej because it's a ball around ei of radius 1 by root 2. It's just a half distance between ei and ej. Ei and this ej, the distance is root 2. Okay, it's actually a distance between I and it's actually a distance of root 2 by 2 between ei and xi. So xi is not equal to xj when I not equal to j. Okay. Cannot be equal to j. This is 1 1. Okay. Now it's clear. Now you define a map from ei domain. That's what we need. Now this then there exists a map from ei can be mapped to xi. Mapped to the corresponding. It's clear, no? It's clear, it's countable. This is just a countable set. Map from this provides a bijection from ei into a subset of n. Okay, you just collect all those I. Okay, but then this is xi is contained in the bigger set, no? Xi, so it's just clear. Is okay?
Yes.
Okay. Okay. So
Yeah, this is fine.
this is fine. So maybe I will stop here. I want to do something more. Can I take some more time? I will prove this Rees lemma and then stop. Okay. I will quickly prove Rees lemma. So this is all about orthonormal basis. Is there anything else I have to do about orthonormal basis? I have asked you to present something wherever there is a gap. Most of the thing I have done, but I want you to do more rigorously. So I have asked you to present something on orthonormal basis. So that is an orthonormal basis. I think we have proved everything about orthonormal basis. If that presentation is done. Okay, let us go to Rees lemma. I'll prove this quickly. So H be a Hilbert space. We have a Hilbert space. Then for x in H, define phi x from H to C by phi x of y equal to yx. Okay. So then phi x of y is linear. Then phi x is linear. That is clear because the inner product is linear. If you take alpha y, you will have alpha here, then you can take it out. And if you have y1 plus y2, then it will come out as 1. It's clear, it's linear. Okay. And I want to show it's bounded also. It's a bounded linear function. So mod of phi x y, okay, this is equal to yx mod of this by Cauchy-Schwarz inequality. This is less than or equal to norm by norm x. Okay. So norm of phi x is less than or equal to norm x. Okay. It's bounded. In particular, it's bounded. Okay. It's bounded. On the other hand, phi x of x by norm x, if you take, that is equal to x by norm x, which is just norm x squared by x, norm x, equal to norm x. Okay, this has norm 1, x by norm x has norm 1. We have already noticed. Okay, so the norm is attained there. So this implies norm of phi x. This is how we will always prove norm is equal to something. We will prove this inequality. This norm of phi x is less than or equal to whatever the norm we want to prove. Then we will prove that norm is attained at some for some vector. So this implies norm of Vx equal to this. Okay. So this phi x going to phi x, this gives an isometry between norm. I mean, if at all, if you take the collection of all phi x, that's the vector space, and this gives a isometry, but this is not linear. That's what I want to say. So this is the proposition. This is what is Rees lemma is, or Rees lemma. Every linear function will look like that. That is the linear. X going to phi x is an conjugate linear or anti-linear, whatever it's called. Okay, conjugate linear isometry from H to H star. Okay, I mean by isometry I mean it's isomorphism also. Okay, it's onto also from H onto H star. Okay, this is what is Rees lemma is. I'll quickly prove this. We have already noticed that that going to that is it's clearly a conjugate linear. I mean, it's clear that phi of alpha x plus beta y equal to alpha bar phi x plus beta bar phi y. I mean, you have just inserted the x in the inner product in the place where the inner product is conjugate linear. So you will get alpha x plus beta y there. Okay. Then you take it out and you will get this. So it's clearly conjugate linear. The map going x going to this implies x going to phi x is conjugate linear. That is what conjugate linear is. Okay. It's a linear map, but then it's a, I mean it will preserve the summation. Okay, and scalar will come out as a bar. Scalar will come out as the conjugate. Okay, so x going to phi x is conjugate linear. Okay, and it's clearly isometric. And norm phi x, we have proved that norm phi x is equal to norm x, so it's isometric. All we have to prove that it's onto. Okay, and isometric is automatically 1, 1. You don't have to worry about injectivity. I mean, if phi x equal to 0, then x is also 0. Okay, it's a linear map. I mean, for linear map, it's enough to verify that phi x equal to 0, x equal to 0. Okay, it's enough to verify the injectivity at 0. Okay, something is equal to 0, then that is 0. So it's isometric is clear. All we have to prove it's onto. Okay, to prove x going to phi x is onto H star. That's what we want to do. If you have any linear map, then it looks like phi x for something else. Okay, for that, suppose phi is in H star. Suppose we have a linear map, phi is in H star. Okay, and phi is not equal to 0. We can assume because the corresponding 0 will, phi 0 will give the 0 map. So we assume phi not equal to 0. Then kernel of phi, which is equal to all those x in H, such that phi of x equal to 0. Okay, this is a closed subspace and it's proper. It's contained in H but not equal to H. If it is equal to H, then phi is 0. Phi is identically equal to 0. And it's closed because phi is continuous. Okay, closed because since continuous. It is just the inverse image of singleton 0. So since it is closed, it is continuous, and it's clear it's subspace, and it's a proper subspace. Okay, now choose some x orthogonal to kernel of. Okay. I mean, if it and x not equal to 0. And if you want and assume, I mean, since we can divide it by some scalar, assume that phi of x equal to 1. Otherwise, you divide it by, I mean, phi of x is not equal to 0. Okay, phi of x is not equal to 0. So if phi of x is not equal to 1, you divide it by phi of x, and you get phi. I mean, you take x by phi of x. That will have phi equal to 1. Okay, so since phi of x is not equal to 0, you can choose phi of x equal to 1. Phi of x, I mean, x is orthogonal to kernel of phi, so it's not in kernel of phi, and it's not equal to 0. Okay, so phi of x, you can assume that phi of x is not equal to 1. Okay. Now, for all for all y in H, I believe, y minus phi of x minus, x minus phi of x times y. Okay, you consider this. Call this is in kernel of, since of course phi of x minus, this should be y. I'm sorry. It should be sorry. It should be y minus y minus phi of y times x. That is there. This is because you just apply phi on that, which is just phi of y minus, if you apply phi of y, you will get phi of y, and phi of x is 1, equal to 1. So this is equal to 0. If you apply that, you get this. Okay? So this is in kernel of phi. Okay? So this implies x is orthogonal to y minus phi of y x. That is x, y minus phi of y x equals 0. So this implies x, y, x, y. I mean, maybe I'll write the other way. So orthogonality, you can write it whichever way. X equals 0. Okay? That is y x minus I take the phi of y out. This is just you get norm x square equals 0. This implies phi of y equal to y x by norm x square. X by norm x square, right? X by norm x square. No, that's not correct. No, there's something missing there. It should be phi of x. No, sorry. What is missing there? X is orthogonal to y, phi of y x, right? So y x phi of y.
So this is
I have written something wrong.
This is fine, sir. If we take t as x by norm x square, then this is phi t of y, right? So it's the form.
No, no.
The,
Y, the norm is equal to 1. This makes the norm of x equals 1. Oh, that's okay. But no, phi of x. This is right, no?
yes, sir. Yes, sir. So we can just define a new vector t as x by norm x.
We have to define a new vector. That vector has norm 1. That is what I'm. Phi of y equal to phi of x by norm x square, right? That's what this is.
Yes.
Sorry, p equal to, sorry, p itself equal to. Right? No, there is one problem here because this has norm 1. Why norm phi has to be 1? We haven't assumed that. There is some problem somewhere. I made a mistake somewhere. This says that the norm of x is 1, no? I mean, norm of phi
So,
itself, which we haven't assumed.
so norm of this thing, norm of
sorry. This
x
is
by
x
norm
by
x
norm x
square is
square.
not 1, right?
Right. No, there's no problem.
Yeah.
It's not
Yeah.
sorry. Yeah. This is norm x square, so it's okay. X by norm x square. So this is okay.
Yes.
So this is okay. No problem. Sorry. Only it's not x by norm x. Okay. This is fine. Okay. X by norm x square. Okay. So that's all. Please lemma is true. Okay, I'm sorry. I got unnecessarily confused. Okay. So this is fine. So we will meet the next class. I'm sorry, I didn't sleep properly. So I am getting confused, quite confused. Okay, my eyes are really burned. Okay, see you. Bye. Good. I will end the meeting. So someone should tell me who wants the dinner product. Okay, bye. Good night.